Hello, today we're going to take a look at it's chapter 11, section 5, and what conservation of angular momentum means. It's a pretty quick concept, so we're going to just review the main ideas here. So let's go ahead and start. If you guys remember, please make sure that you're checking the notes that I've posted online as well for section 11.5. They're pretty short. They're only 2 pages, and I think it gets the idea across pretty quickly. So the main idea is, remember here, we've got momentum. Momentum is mv. You know that. We've been using that for a while now. And if you remember, if there's no force, if there's no net force, then the change in momentum was 0. And what we would say is that the net force comes about by a change in momentum with respect to time. And if we put a vector arrow over it, we see it deals with vectors. So what we have is momentum. If it changes, there must be a net force. So if there's 0 net force, then you have 0 change in momentum, right? That must mean the momentum is the same. So basically, if your net force is 0, that means nothing external is trying to change the system, and therefore it doesn't change the momentum. Well, the same logic essentially applies here. Since we know that angular momentum is r cross p, and we'll put vector arrows on that, we also know that the torque is the change in angular momentum with respect to time. If you want, you can also think about it algebraically, but I think it's better to think about it as a vector. And in fact, I don't really want to write that because then we're not really dealing with vectors anymore. Okay, so the point is that torque is the change in angular momentum, kind of similar to force is the change in linear momentum with respect to time. So what we end up seeing is if you have 0 torque, then you have 0 change in angular momentum. So basically, if the net torque is 0, then the angular momentum will stay constant. And then this is where it gets kind of interesting. And I don't mean mathematically it's difficult or anything like that, but it gets conceptually interesting. Because if, let me center my board here, if the net torque is 0, then there is no change in angular momentum. Okay, so that doesn't mean the angular momentum is 0. It just means that it doesn't change. So this gives us a really interesting setup. You could have angular momentum initial and then an angular momentum final that's the exact same amount. So you might be wondering, what do you mean by initial and final? Well, let's say an object changes its shape while it's rotating. It would keep the same angular momentum because nothing external came over to the object and changed its shape. It was something done internal, like you put your arms out or something like that. So the angular momentum doesn't change because there's no net torque, but you spin faster or slower. So how do we explain that? Well, think about it like this. I initial, omega initial, and I final, omega final. I'm just going to go ahead and drop the vectors at this point because we're just going to talk about it conceptually here for a moment. So basically, the total angular momentum doesn't change if the net torque is 0. But what might change is the moment of inertia. So like, let's say you put your arms out and the moment of inertia gets bigger. That means your angular speed will get smaller because you got to balance and still have the same total number. Or you could go the other way. You could make your moment of inertia get smaller, and then your angular speed gets larger. So this is why if you bring your arms in when you're spinning, you'll go faster. If you put your arms out, you'll go slower. I was going to demonstrate this for you guys. I linked some videos that demonstrated it. But try it out yourself. If you have a spinning chair, grab 2 books because that puts mass in your hands and that gets it further away from your body. And try spinning up the chair while you sit in it and put your arms out and in, and you'll find you'll go faster and slower. It's kind of a good home experiment that you can do. So basically what ends up happening if you have conservation of angular momentum problems is you know the total angular momentum at the beginning and the end are the same. It's just a matter of, dealing with that, okay? So typically what ends up happening in this section is you use either this, or you might use something like RMV equals RMV. I guess the mass could be final, initial, and final, but that would be kind of weird, because if you had a single object and it changed its mass, that should change its angular momentum. So maybe if you had two objects and one object gave some of its mass to the other object, but the total mass doesn't change, then you could have something like this, where maybe the radius gets bigger or smaller, and therefore the velocity gets bigger or smaller. You can kind of see it here. It's the same idea in either one of these lines. It's the same basic concept, that we're looking at a change in some kind of R that gives us a change in some kind of V. Because remember, omega is just V over R. So if I is mr squared or half mr squared or something like that. So you really are changing R and V quite often. The mass could change, but you would need two objects and one mass like split apart into two masses or something like that, but you're still keeping the total angular momentum consistent. Okay, so the last thing I think to mention on this is to take a look at what happens when objects stick together. And I think I linked a video or an example that goes over that. So the last thing is, what do you do if you have, like, I don't know, let's say you have, this is a pretty classic problem. You have like a board, and this is a pivot point here, and there's like some kind of object traveling towards the board. And then after it collides with the board, let's say it sticks together right there, and then the whole thing starts to rotate. Well, we know that there's angular momentum. Let me scoot this up. We know there's angular momentum of this little particle traveling forward with respect to this point. Look at number 27, and our bell work talks a little bit about this. But since this thing isn't moving at all, it starts with zero angular momentum. This thing here starts with all of the angular momentum. And then let's say they collide and stick together. Now together they will rotate, or let's say around this point, and together they still maintain the same angular momentum you had before the collision. So basically it's a lot like before, where you had, if you remember, linear momentum was kind of like this. So this might be like object one, object two, and then when they stuck together, you would do like a thing like this and V final. In fact, if that's object one and that's object two, well, that shouldn't be a plus. I'm sorry. It should be multiply. Right? So let's say that's the board, that's the little particle. After they stick together, if they were linear, it'd be really simple. You would just move them in a straight line together. But that doesn't apply here. What we want to do here is take a look at the angular momentum conservation. So we could have something like, for an angular momentum, maybe we have I initial, omega initial of the first object, and I initial, omega initial of the second object. And then at the end, there's just some total final thing, because they're stuck together. Maybe you get a new moment of inertia, and so therefore a new angular speed. Maybe this thing doesn't have an angular speed, and this just has a linear speed. And you have to think about how far away is it from this point right before it hits that thing. Okay, so there's all kinds of little ways you could look at it, but it's really the same concept, that you're doing kind of the total angular momentum doesn't change. Okay, so there's a lot of different ways you can apply this, but it really, really boils down to this basic concept, that if there's no external torque, there is no change in angular momentum, but what you can change is the shape. So if you make the shape bigger, whatever the object is, your angular momentum will stay the same, but your angular speed will go down. Make the shape smaller, angular momentum stays the same, but your angular speed will go up. All right, I hope this helps. We'll do a help session next week, probably on Monday, and I will see you guys.